Welcome back to Chapter 3 of U.S. Power Squadron Sail Course. This chapter we'll be working on boat design and hull types. Boat designers have long sought after the ability to design the perfect boat. If that were attainable, we wouldn't have the thousands of designs that exist today. The constraints of design are really built into three things. We're looking for the design to be able to limit leeway, that's sliding, and yet also satisfy the general type and use in its intended use. The different factors that come into the design are often trade-offs that we have to choose the optimal of these various balancing acts, let's say. What are our purpose? What are we trying to build a boat for? Are we trying to have a day sailor? Do we want to have a racer? Do we want something that's going to be fun for weekend cruising? Or is it something that we're going to want to live on for a long time and sail offshore? Size of the boat is another factor, but it also affects costs, but it also has a trade-off for comfort. Larger boats have room for more people, but they are more expensive. Sizes range from small, opties that are 8 feet long to very large boats. Large day sailors are in the 12 to 30 foot range, such as sunfish, lasers, flying Scots, thistles, and Malgus 30s. Our coastal cruisers are 20 feet or more, and may have some limited cooking and cooling, storage, and sleeping accommodations on them. For offshore cruising, we want to be able to being out on the water for an extended period of time, several weeks or more, and be able to handle bad weather, because if you're on the water that long, you're going to experience some bad weather. Aesthetics are sort of an eye of the beholder. There are a couple factors that come into play are freeboard, which is the distance from the water line to the top of the deck, and then shear, which is the slope of the boat front to back. In addition, our hull shape will also be a factor of design. What we're trying to do is trying to minimize the water resistance and maximize the leeway resistance, which is the ability to shift sideways when the wind is blowing. In this boat, we can really see what the freeboard is like. And what the freeboard is this space right here between our water line and the top edge of the deck. That's the distance. And the more freeboard you have, the drier the ride is. If you remember when we were riding on a laser that has got freeboard of about 4 inches, it's a very, very wet ride. Whereas on this boat, you would be dry most of the time, except when you're in a really big blow. This boat has a really good example of the shear line. And so what we've got here is the shear is this line that runs across the deck front to back, and it kind of gives it a salty look to it. Boat designers are going to really look at what material is readily available, whether that be in the early days where they made boats out of reeds or wood, and now fiberglass. Wood and fiberglass now are the predominant building material for boats that we would have in our area. Aluminum, steel, and ferro cement boats are also used for larger boats. It's hard to imagine that building a cement boat a boat out of cement would be something that people would want, but it's true. And the designs, of course, are going to vary based upon the intended purpose of the boat. The keels evolved, also from, full-length keels to a bulb or wing. And the point of that is to really prevent leeway, which is the sliding of the boat sideways based upon the wind. The length of the boat really determines its maximum speed. So we're talking about displacement boats here. In displacement boats, the speed is 1.34 times the square root of the waterline length in feet. So that determines our speed, and that's offset by the wetted surface area, which is the water friction. And the wetted surface area is that part of the boat that is underwater. Here are generally the steps in building a fiberglass boat. You start out with a mold, which is a shape that you want it to ultimately be. It's like an ice cube tray or a plaster Paris tray where you're going to, that's going to form the shape of the hull. Then you apply a coat of gel coat to the mold. That's the outside finish cover that you're going to see when we're all done. Then on top of the gel coat, you're going to apply some fiberglass material. The number of layers of fiberglass material will determine its strength. Sometimes we add core material like a balsa wood or foam to add thickness without adding a lot of extra weight. After you've done that, then we apply the resin on top of the cloth, fully saturating it, put the hardener in with the resin, and then wait for it to cure. When the boat is cured, then you can remove the hull from the mold. This boat here has just been taken out of the mold and is now having the extra finishing touches put on the decking. A couple of more factors in the hull design is the entry angle, and that's how sharp this angle is here and how well it will then cut through the waves in the water. Most boats will start out at the beam, which is a cross section at its widest point, and then start moving down, adding on to create its ultimate underwater or hull shape design. The design of the keel is also an important factor in designing the boat. And the keel reduces the leeway, which is the sideways slipping, as well as lowers the center of gravity. The keels are usually weighted to lower the center of gravity, and they're weighted with ballast, which is in the keel is usually made out of iron or lead or something like that. Boat designs have various hull configurations, such as the full keel, a full keel with a cutaway forefoot, a fin keel with a balanced rudder, a fin keel with a skeg rudder, a centerboard hull, a dagger board, a lee board. We're going to look at each one of these in more detail. Here are some diagrams of the different underwater shapes of boats with different keels and rudder arrangements. And we're going to look at the pros and cons of each one of these in the next slide. Here we have the full keel. Now the advantage of the full keel is that it tends to stay in a straight line, and its extra underwater surface makes it slow to tack and has a slower speed. The full keel with a cutaway forefoot is kind of a compromise between the full keel and a fin keel system. It still sails straight, but it's maybe just a little bit more responsive. In this boat, we have a picture of a fin keel with a skeg rudder. The skeg is part of the rudder that helps protect it in case you run into something. Here is an illustration of a fin keel with a spade rudder. These are the ones that we're most likely to see in Central Illinois as well as coastal cruisers. The fin keel provides good, makes it handle well. It sails well to windward. It's quick to tack. The disadvantage is it doesn't stay on track so well, so you have to concentrate more on steering it. And it also has the fin keel tends to be deeper, and so you'll have to worry about the depth of the water that you're sailing in. According to Archimedes' principle, the weight of a boat is equal to the weight of the amount of water displaced by the hull. In these boats, we can see that the different keels have different centers of gravity because of ballast, which is weight added by lead or steel to lower the center of gravity. The ballast displacement ratio is a key factor in determining the ability to decide how much sail you can carry safely. So for example, in the ballast displacement ratio for a star class boat, the ballast is 900 pounds on that boat. The displacement is 1,460, so that's how much the boat weighs. And so the balanced displacement ratio would be 0.616. This means that 62% of the weight of the boat is in ballast, which really provides the most benefit. More recent innovation is actually changing the design of the keel itself, adding trim tabs or winglets on the outside. Here is a picture of a boat with a wing keel. If you look at the bottom of it, it actually looks like a wing. And this would be similar to the keel on my Capri 22. This is an example of a boat with water ballast. In this kind of situation, the water ballast can be pumped to the high side, which can then actually add stability while you're in the water. When it's out of the water and put on a trailer, the water is drained out, which then makes it easier to transport. In this slide, it illustrates a boat that uses a centerboard to provide stability, leeward stability. This would be used in some, in boats like a San Juan 21, a Flying Scot, or a Thistle, and many others. The primary characteristic of a centerboard is it rotates around a pin and then is pulled up and down by way of a pendant. So when you're off the wind, you can maybe raise the centerboard up, or when you're pulling it out of the water, you would pull the centerboard up into a trunk. And then when you're out going upwind, you can lower the centerboard to provide the stability that we need and to keep it from slipping too much sideways. This illustrates an example of a boat using a dagger board. A dagger board goes through the hull like a dagger and is held in place by friction. Boats using dagger boards are similar to Sunfish, Lasers, our Optimus, all use dagger boards to keep the boat, and they provide the same functionality as a centerboard in keeping the boat from sliding sideways in the wind. This slide has a picture of a boat that's using lee boards. That's these deals right here on the side, and they provide the same functionality as a dagger board or a centerboard. Here's a picture of a boat with bilge boards, and these have keels that are right over here on both sides of the boat and provide stability when the tide goes out. It keeps the boat upright. It also provides greater depth when the boat's heeled, then the keel goes down deeper in the water. We also see this type of arrangement on MC scows and sea scows. Here we have an example of a catamaran. If you compare a catamaran to monohull, they have higher initial stability because their beam keeps them upright. They're wider apart. So there's also less water resistance, and therefore they're faster. But they're more difficult to tack because they have a whole lot of more area to transfer through. Trimarans are similar to catamarans in their tacking ability. And the reason they tack slow is because they have such a long ways to go from this direction all the way over to that direction. On smaller boats, we're likely to see transom hung rudders that are attached to the back of the boat. The rudder then is attached to the stern through a gudgeon, which is an eye of the boat, which are these parts here, with some pintles, which are little pins that fit in the circles on the gudgeon. Those allow the rudder to turn, the rudder head with the tiller, and so they can turn it side by side. And these are done on small boats. Here's an example of a sailboard. Now these are very fast. They're simply a surfboard with a sail attached to them. The sail has a wishbone boom, no rudder. The steering is done by moving the center of effort forward and aft to turn the boat. Let's finish up this section by going over some of the vocabulary. Ballast, which is the weight to help improve trim stability, and it's very, very low in the boat. A board is just a little boat like a Sunfish, which you can carry on the top of a car. A centerboard is a pivoting board that can be lowered through a slot in the keel to reduce leeway. A dagger board is like a centerboard, only it slides straight through the hull to reduce leeway. Displacement is the weight of water displaced by a floating vessel and the weight of the vessel itself. A gudgeon and pintle are really a metal eye and a matching pin used to mount the rudder on the transom of a boat. Leeway is the sideways movement of the boat through the water caused by wind or current. A stringer is a fore and aft structural member of the hull. A tiller is the lever that's attached to the rudder used by the helmsman to turn the boat. And wetted surface is the portion of the vessel's exterior part which is in contact with the water. This concludes Section 3, Boat Design and Hull Types. Our next chapter will be on standing rigging.